Okay, actually thinking about it, because I'm looking at this equation, I think I'm doing something wrong. Hey, what's going on, guys? How are you doing? For those of you who are new here, welcome to my channel. I'm Lathan, and I'm currently working as a data scientist. Today's video is one that I'm pretty excited about, and it's going to be me as a current data scientist attempting to take the US high school AP statistics exam. So a brief spiel about what AP is for those of you who are outside of the US watching. It's basically a standardized test, so similar to A-levels if you're in the UK, where you basically take these courses, these additional courses at the high school level that teach the subject matter at supposedly a college level. And if you successfully pass these courses, some colleges will accept AP credit such that you can place out of introductory courses in that subject. So the reason I had this idea of taking the AP Stats exam is that, I remember back in high school, data science as a career or, anything in that sort of quantitative realm wasn't even an option for me. I mean, I remember in high school, I was pretty aggressively pre-med. I thought, medicine was pretty much the only thing I could see myself doing. And I think part of that was I wasn't really exposed to data science or statistics or anything in that sort of quantitative realm. We had this class, so AP Statistics, my high school offered AP Statistics, and mostly seniors were allowed to have the option to take AP Statistics or not. So I was one of the high school seniors who decided to take AP Stats. And I remember thinking, AP Stats was this class that not a lot of people really cared about. And I think it was really unfortunate that we had this really good teacher. It was her first year teaching. So when I took AP Stats, it was her first year teaching. And she taught us for about a month, I want to say, and it was pretty good. But then unfortunately, she was diagnosed with leukemia, and then she had to take a leave of absence. So at that point, my high school was scrambling to find replacements and substitute teachers for AP Stats, but they couldn't find any. So what they ended up doing was they ended up rounding up the other math teachers who did not have statistics backgrounds. They did not have formal sort of intense statistical training. But they got these teachers and told them, okay, now you have to teach this course. You have to teach AP Statistics to high school students. And let me tell you, teaching statistics is hard. It's not easy. These teachers, they probably had some exposure to statistics in college. Maybe they took, a class here or there. But it's really difficult to teach statistics. And there's a lot of sort of theory and pedagogy that goes into teaching stats. So what ended up happening was the class sort of became a joke, and none of us really took AP Stats seriously. I mean, the teachers didn't really know how to teach it. They didn't really know what they were doing. So we ended up going the whole year sort of doing kind of, pseudo stats up until the AP exam, which was, I think it's in May or something, or June. And a couple weeks before, everyone started realizing okay, this exam is coming up soon. We don't know any statistics. We gotta start doing something. So pretty much all of us just bought the Barron's AP Stats book and we just crammed for the exam. So I ended up getting a 4 out of 5 on the exam, which was not bad considering I just pretty much crammed the entire test's worth of material in a couple of weeks. But after that exam, I thought, okay, stats isn't really for me. I didn't really get much out of it. And I didn't really think to pursue stats as a career. So fast forward, I don't know, 5-6 years, who would have thought that I'd be using stats in my everyday life as a data scientist? So what better way to go full circle and try to take this AP Stats exam that, I found kind of difficult back in high school, but now that I'm a data scientist and use statistics literally every day, let's see how it goes. Okay, so after some Googling, I was only able to find AP practice exam questions, but the free response ones, so not the multiple choice ones. So I found this paper from 2018. So this was the official College Board. That's like the organization that runs these AP tests. The official College Board 2018 AP Stats free response questions. So let's see how it goes. Okay, this is nice. Yeah, they give you all the formulas for the descriptive stats, the probability, some inferential statistics. Okay, that's good because to be honest, a lot of the times like I don't even think I know the formulas off the top of my head. Usually the functions that I use in R has all that already programmed into it, so I don't have to think about the formulas from first principles. So it's good. It's good that they do that because otherwise it'd be pretty hard. Okay, so question 1. The manager of a grocery store selects a random sample of 11 customers to investigate the relationship between the number of customers in a checkout line and the time to finish checkout. Okay, blah, blah, blah. Data are shown in the following scatter plot along with the corresponding least squares regression line and computer output. Okay, so we have a graph, a scatter plot with a line through it. The x-axis is customers in line, and the y-axis is time to finish checkout in seconds. And we have some stats that are already calculated for us. So we have some coefficients, the standard errors of those coefficients, the t-statistic, and the p-value. Okay, so, okay, we also have this s thing, which I don't really know what that is, an r squared and an adjusted r squared. Okay, so the first question, identify and interpret in context the estimate for the least squares regression line. Okay, so if we write out this equation, so we can just write it out in our trusty y equals mx plus b. Oh, let me also label the questions. So our least squares regression line is going to be y equals 174.40 x plus 72.95, and this question is asking us to identify and interpret the intercept. So the intercept is 72.95, and what that represents is basically so when there are 0 customers in line, and I'm also just gonna write in shorthand because I don't want to write it all out. When there's 0 customers in line, the average time, average is the key word here, the average time to finish checkout is 72.95 seconds. Okay, and I think that's it for part A. So part B, identify and interpret in context the coefficient of determination, r squared. So to identify it, it's pretty easy because in the table they tell us r squared is equal to 73.33%. We're not going to worry about the adjusted r squared for now. And what that means is, so how you interpret this coefficient of determination is it's basically you can say 73.33% of the variability in your dependent variable, so that's like your y variable, in this case that's the time to finish checkout, is explained by the independent variable, or your predictor variable, or your x variable. There's a lot of different names, but in this case it would be the number of customers. Okay, and I think that's it for part B. Part C, okay, one of the data points was determined to be an outlier. Circle a point on the scatter plot and explain why the point is considered an outlier. So that point is basically going to be the point, so let me just draw it out. We have like a bunch of dots, and then there's like this dot like at 0.3 and pretty close to 0. So this is the outlier. And outliers in statistics, there's actually a whole lot of math that goes towards identifying what an outlier is. If I remember correctly, though, in AP Stats, they don't really go into that math or that theory about identifying what's an outlier and what isn't. So I think for the purposes of this AP Stats question, we can probably just say, that point is an outlier simply because it deviates from the pattern. So I'm just going to write deviates from pattern. And I don't think we need to say anything more than that. Okay, question 2. So an environmental science teacher at a high school with a large population of students wanted to estimate the proportion of students at the school who regularly recycle plastic bottles. The teacher selected a random sample, of students at the school to survey. Each selected student went into the teacher's office one at a time and was asked to respond yes or no to the following question: do you regularly recycle plastic bottles? Based on the responses, a 95% confidence interval for the proportion of all students at the school who would respond yes to the question was calculated as 0.584, 0.186. Okay, and then the first question here is, how many students in this sample were selected by the environmental science teacher? Okay, so there's kind of a lot going on in this question. I feel like there's going to be a lot of math. So I'm just going to start writing stuff down. So it's asking us to find n, and we have a 95% confidence interval for a proportion as 0.584 and 0.816. So really quickly, I think the formula for a one sample proportion confidence interval is our proportion plus minus our test statistic times the square root of p times 1 minus p over n. Actually, let's check the formula sheet. Yeah. Okay. Great. Yeah. So this is how you write the formula for a confidence interval, and we can actually calculate our proportion. So with confidence intervals for proportions, it's pretty much the middle of the confidence interval. So because it's the middle, we can just do 0.584 plus 0.816 divided by 2. I'm just going to use my calculator to calculate that. 0.584 plus 0.816 divided by 2, and that gives us 0.7. Okay, so we have our p, these should be hats, and our z is going to be 1.96 because that's just like a number that you have to know. It's 1.96 for a 95% confidence interval. So when we do that, I think we can just start plugging everything in to find this value. So we have 0.7 plus minus 1.96 times 0.7 times 1 minus 0.7 over n. Oh my god, there's going to be, but we need to set it equal to something. So I think what we can do is, we set it equal to, so I think what we can do is, if we take one limit, so the upper bound, we can then set it to the upper bound, and then we get 1.96, 0.7 times 1 minus 0.7 over n equals, and we just subtracted 0.7 from both sides, and we get 0.116. Okay, so yeah, this is pretty much just a lot of math. I'm going to plug this in the calculator, and I'll be right back. Okay, so it turns out that we get n equals about 59.95. So we're just going to round this up to 60. And that should be our answer. We need a sample size, or not need, but the teacher had a sample size of 60. Okay, that was a lot of math. Next part. So the next question asks, given the method used by the environmental science teacher to collect the responses, explain how bias might have been introduced and describe how the bias might affect the point estimate of the proportion of all students at the school who would respond yes to the question. Oh, okay, so this is interesting. Yeah, I remember this part of the AP Stats exam, where it's kind of a hard concept to grasp. Like, bias is a hard concept to grasp, especially for high school students. Like, so many professionals, even like statisticians and epidemiologists and data scientists, struggle with bias. There's so many times when we're just blinded by our biases. So yeah, this is kind of a tricky question. I think there are a lot of potentially right answers. Basically, bias is thinking about something that might have adversely swung the results one way or the other. So I think here, let me think about this. I think one potential bias. So it says, if we go back to the question, so it says that each selected student went into the teacher's office one at a time and was asked to respond yes or no to that question. So I think there might be something, I think this is called like responder bias. And basically, these students might not be truthful because, they're talking to this environmental science teacher. So they know that this teacher is super, cares a lot about the environment. And if he asks, do you recycle? And a kid says no, that kid might be scared, like, oh man, is he gonna hate me? Is my answer going to negatively affect a relationship? And this is a real effect that people have observed. I think it's called responder bias. So generally in these situations, like in the real world, you don't want to have someone in a position of power or influence asking these questions. You want to send out anonymized questionnaires. This is to try to reduce as much of this potential bias effect as possible. So yeah, I'm going to write down responder bias and how it might affect the point estimate. Well, basically, with this responder bias, you're going to have more students say yes to recycling, even when in reality they might not recycle. And that is going to result in a higher proportion of students. So yeah, I think that's pretty much it. Okay, part C. So part C, oh my God, there's so many words. Statistics teacher at the high school is concerned about the potential bias in the survey. Great. To obtain a potentially less biased estimate of the proportion, the stats teacher used an alternate method for collecting student responses. Random sample of 300 students was selected, and each student was given the following instructions on how to respond to a question. In private, flip a fair coin. If heads, you must respond no, regardless of whether you regularly recycle. And if tails, please truthfully respond yes or no. What is the expected number of students from the sample of 300 who would be required to respond no because the coin flip resulted in heads? Okay, so that's a probability question, and I think, yeah, I'm pretty sure you can just do, so the expected number, when they ask for expected number, that's, you basically take your sample and you multiply by the probability of that event. So the event is the coin flip resulting in heads. If it's a fair coin, that probability is 1/2. So 150, I think, is the answer for the expected number of students. So if we move on to the next one, the results of the sample show that 213 of the 300 selected students responded no. Based on the results of the sample, give a point estimate for the proportion of all students at the high school who would respond yes to the question. So yeah, they even underline stuff because I think there's a lot of words here, a lot of potential to go wrong. So I think to answer this question, so how many, okay, so we have 213 out of 300 no's, which means if we, let's see, if we take this 213 number and subtract it from this expected 150, we get 63 students based on our expectation who truthfully said no. So I think that means we would expect from this expected 150, so if 63 truthfully said no, it means that the other 87 truthfully said yes. So based on this expected number of students who would respond no, no, so out of the students, expected number of students who responded no, 87 truthfully responded yes, and that would be the proportion of all students at the high school who would respond yes to the question. So whatever that proportion is, 0.58. I think that's our answer. Okay, question 3. Let's do this. So it says approximately 3.5% of all children born in a certain region are from multiple births. Okay, of the children born in the region who are from multiple births, 22% are left-handed. Of the children born in the region who are from single births, 11% are left-handed. Okay, so the first question is asking us, what is the probability that a randomly selected child born in the region is left-handed? Okay, yeah, this is pure probability. So let's write out this question in the form of a probability equation. So it's asking us, what is the probability of being left-handed? And there are a couple ways that you can be left-handed. You can be left-handed from a multiple birth. So you would write that as the probability that you were born from a multiple birth times the probability of being left-handed from a multiple birth. Another way you can be left-handed is you can be from a single birth, and again you can be the probability of being left-handed from a single birth. So we can now just start plugging our numbers in. So I think it gave us this 0.35% times and I think it gave us 22%. And for the single, so how you get the single birth, you just subtract 3.5% from 100%, so you get 0.965, and they give us this other number of 11%. So you just plug that into a calculator, which I'll skip over, 0.113. And Yeah, I think that's your answer. That's 11.3% of being left-handed. So the next question asks, what is the probability that a randomly selected child born in the region is a child from a multiple birth given that the child selected is left-handed? So this is asking us, so again, we write it out in our probability way, and it's asking what is the probability that you're from a multiple birth given, this line denotes conditional on being left-handed. So this is, so conditional probability, there's an equation, I believe it's called Bayes' theorem. So let me just find that equation. Yeah, it's definitely a good equation to know. Like people in my field use it all the time. And basically it's, so let me just write out the equation here. It's P of A given B, or event A given event B, is equal to the probability of event A and event B occurring together divided by the probability of event B. So when we write it out in our scenario here, it's the probability of being from a multiple birth and being left-handed all over the probability of being left-handed. So we have the probability of being multiple and being left, assuming they're independent. So we have 0.035 times 0.22. Those numbers were given to us. And then we can actually use the answer from part A, which was 0.113. And we plug that all in, and again, I'm gonna skip over the math, but basically we get 0.068. So that's 6.8%. Cool. Next part is, let's see, okay, so we have a random sample of 20 children born in the region will be selected. What is the probability that the sample will have at least 3 children who are left-handed? Okay, so, oh man. So, okay, this is okay, I think I remember this from my stats courses. This is an at least problem. So if it's an at least problem, you can solve that using the binomial equation. So it's asking us for the probability of at least 3 left-handed. Yeah, I don't know the binomial equations off the top of my head, so let's go back to our equation sheet and see if they have the binomial equation. Okay, yeah, they have this equation for the binomial distribution. So, okay, I think we have to rewrite it, because if we use this equation, then we're going to technically have to calculate the probability that you get 3 children, the probability that you get 4 children, 5 children, 6 children, all the way up to infinity. And we're not doing that. So you can rewrite this. This probability is the same as the probability of 1 minus the probability of less than 3 left-handed. Or 1 minus, since we're in discrete terms, less than or equal to 2 left-handed. So we can rewrite it like that. And then it's just a matter of plugging in our equation, the binomial equation. So I'm just going to fast forward through this part. Okay, so yeah, definitely can't calculate this by hand. I think during the AP Stats exam, you have access to like a TI-84 calculator or something. I don't have one of those anymore. So I'm just gonna plug this into like Wolfram Alpha on my computer, or R even, and I'll just go through that. Okay, so the answer is about 0.40, and that's pretty much our probability, 40%. Question 3, done. Okay, I think we're about halfway through this exam. Yeah, I forgot how long the AP Stats exam can feel, just because there's so many words, and there's a lot to sort of process and try to tease out the important information that you can use to solve the question. But anyway, let's get into question 4. So the ACL, okay, blah, 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 some background. To test the effectiveness of the new procedure, a study was conducted in which 210 patients needing surgery to repair a torn ACL were randomly assigned to receive either the standard procedure or the new procedure. Okay, cool. Based on the design of the study, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction in recovery time compared to the standard procedure for patients similar to those in the study? So yeah, this is actually, this is a key sort of concept in statistics, and that is what constitutes causality. And really, the only way you can establish causality is if you do an experiment, or in sort of translational terms, an RCT, or randomized controlled trial. So based on my understanding of this prompt, it sounds like it is describing an RCT, because the key part is patients were randomly assigned to different groups. That's super important to establish causality. So let's write out some of our evidence. So we have this random assignment, which helps establish causality. And the next part is statistically significant, which what that means sort of conventionally is you do a hypothesis test and your p-value is less than 0.005, and that usually constitutes evidence, sufficient evidence to reject the null hypothesis and conclude that what you have observed is likely not due to chance. That's basically what you're saying. So would a statistically significant result allow the medical center to conclude that we see this effect? Yes. And there's also another key part in this question: for patients similar to those in the study. So this is important because the RCT, even though it establishes causality, you can only generalize as far as your sample of people that you tested, whatever, and can allow. For example, if we conducted an RCT in like white people, we would not necessarily expect the results to generalize to, Asian people living in Taiwan, for example, just because it's a different population of people, and there might be other factors that we haven't accounted for. So you can only generalize as far as your sample allows you to. But because they're really careful in their interpretation, for patients similar to those in the study, I think the overall conclusion is valid. Okay, great. Okay, great. Oh, I think this is question 4. Okay, great. The next one is part B. So it is summary stats on the recovery times from the surgery are shown in this table. So we have our sample size, we have our mean recovery time, standard deviation, okay. Do the data provide convincing statistical evidence that those who receive the new procedure will have less recovery time from the surgery on average than those who receive the standard procedure for patients similar to those in the study? So, okay. Okay, I think there's a couple things going on here. I think we have to. So the first thing with any sort of statistics is you always have to state your null hypothesis. I cannot stress how important that is. A lot of people, when they, run some tests, and it's so easy nowadays with programming languages to just run the command. They don't even know exactly what that p-value represents. They don't know what they're testing. So if you don't know your null hypothesis, your conclusions may not be valid because it may not be the thing that you're actually interested in. So let's go ahead and state our null hypotheses here. Or I think there's just one, yeah. Let's go ahead and state that. So our null hypothesis is that the mean recovery time between the standard treatment, so let's denote this with this Greek letter mu. So the mean recovery time for people who receive the standard treatment should be equal to the mean recovery time for patients who receive this new treatment. In other words, there should be no difference. And the alternative is that we expect the mean recovery time for people who receive the new treatment to be less than the mean recovery time for people who receive the standard treatment. So now that we have our null hypotheses, we have to identify a test that we can do. It's pretty clear to me. This is a 2-sample t-test for a difference of means. So the thing with these statistical tests is they all have different names, and this is one of the most common ones. It's literally called 2-sample t-test for a difference of means. So we're gonna use that. So I think other things that we have to consider, because basically it's asking us, is this evidence compelling? And again, similar to the previous question, one sort of really strong piece of evidence that makes something compelling is the fact that this is an experiment, so it's randomized, and that helps us establish causality or effect. So that's important. I think the other thing to consider, let's see. So I think what this question is asking for is, I think this question is asking us, for something to be convincing, it has to be valid. So the t-test has a couple of assumptions. So this 2-sample t-test, has a couple of assumptions. One is you have large enough sample sizes. The other assumption is that your data have to follow a normal distribution around your mean and your standard deviation or variance. So I think that because we have a large sample size, so we have n equals 110 for one group, and for the standard group, let's denote that with ns, and we have n of the new group is 100. I think we can presume that our means will be, or the distribution of our sample means distribution of sample means is normal. So because that's true, we meet the assumptions of the t-test. So I think because of all these things, so, we have, for the t-test, we have an experimental setup and the assumptions of the t-test are met. We can conclude that the results are convincing evidence for, and then I would just write out the effect if this were the real deal. Oh, and then of course, for patients similar to those in the study. Make sure you write out that. So I remember one thing in the AP Stats exam was that to get full marks, to get full points, you just have to be as thorough with your interpretation as possible. So that was something we didn't learn in my high school class because we didn't really have a thorough, comprehensive stats education in high school. But now that I've been trained in statistics formally and I'm doing it as my day job, really being careful with how you say something, that's absolutely crucial, because it's so easy to sort of leave out something and then the entire interpretation becomes sensationalized. So you might see in news headlines, bread causes autism or something like that. That was just bits of information getting stripped continuously until you're left with something that's false. So it's really important to be super thorough and include all the words that sort of validate your conclusion. Okay, question 5. Okay, so we have a couple of histograms. We have 2 histograms for teaching years for the teachers at 2 high schools. Okay, teaching years recorded as an integer, with first year teachers recorded as 1, and so on. Okay, both sets of data have a mean teaching year of 8.2. High school A has 200 teachers, high school B has 221 teachers. On the histograms, each interval represents possible integer values from the left endpoint up to, but not including, the right endpoint. Okay, got it. So that means, for example, this bar here, it goes from the first year of teaching all the way up to the beginning of the 4th year, but not including the 4th year. Okay, so the first question asks, the median teaching year for one high school is 6 and the median teaching year for the other high school is 7. Identify which high school has each median and justify your answer. Okay. So is it asking us to calculate median? Okay. I don't think it's asking us to calculate median because I don't know how you would do that without the actual raw data. The median is just the halfway point. It's the 50% mark. So I don't know how you would calculate that. So I think it's asking for a more heuristic answer. So my initial thought is that, okay, so let me just sketch out these. Oh my God, that's ugly. Let me just sketch out these histograms. Okay, so this is high school A, and high school B is that. So this is a really bad sketch. But if we were to sort of draw a smooth distribution over it, you'd sort of get something like this. And my intuition is that high school B probably has the lower median. And the reason for that is, let me just write out these numbers. The reason for that is okay, if the mean for both these schools is 8.2, One thing to note about high school B is that this is what we call a right skewed distribution, where the tail on the right side is a lot longer than the tail on the left side. And one property of this is that in these left skewed distributions, the mean is usually much larger, or like a lot larger than the median, because the mean has been dragged up by the tail on the right end. The higher values are dragging up the mean. So we expect the mean to be a lot bigger than the median. So I'm going to go with that as my answer. Yeah, not super, again, like, I think the only way to calculate, maybe there's a way to calculate the median from this histogram. I'm sure, because it's like counts, so you can probably get the median through that. But I think during the exam I would probably do it that way, since I'd probably be pressed for time at this point. So yeah, I'm gonna go with this, and I think that's a totally valid way to describe median. Okay, so part B, an additional 18 teachers were not included with the data recorded from the 200 teachers at high school A. The mean teaching year of the 18 teachers is 2.5. What is the mean teaching year for all 218 teachers at high school A? Okay, so this is like a weighted average problem. That's what it's asking for. And how you calculate weighted average is you just take the sample size from one sample from one group, multiply it by the mean of that group, and then you add sort of this new group, so this new group of 18 teachers and their mean, and you divide it by the total number of people that you're considering. So if we plug that into a calculator, we get 7.7 years. And I think that's it. That was pretty straightforward. Part C asks, the standard deviation of the teaching year for 221 teachers at high school B is 7.2. So let's write that down, 7.2. If one teacher is selected at random from high school B, what is the probability that the teaching year for the selected teacher will be within one standard deviation of the mean of 8.2? So within 8.2, and then one standard deviation is plus or minus 7.2. So that is 1.1 and what is that, 15.4? And it's asking, okay, what is the probability that the teaching year for that selected teacher is within this range? So I think to do that, we can just add up the counts. So if we literally go through like bar by bar, so the first bar that's like 79, plus the second bar that's like 34-ish. The third bar is like, maybe that's like 27. Hard to tell exactly. The fourth bar is, I'm gonna say that's 29. And then I think we can add the fifth bar too, since it does encompass, it goes up to like 15.40. So even that bar is like technically up to 16. I think you can just use that value. I mean, this is going to be a rough estimate anyway. So 19. And we know that there's a total of 221 teachers at high school B. So again, we do a bunch of math, and that comes out to 0.86. And I think that's it. We are on the last question of the free response section. Oh my gosh, it's been kind of long, but we're almost there. So let's bang it out. Okay, so systolic blood pressure. Okay, amount of pressure that blood exerts on the blood vessels. Okay, the mean is 122 millimeters of mercury. Standard deviation is 15. Let's write out. Yeah, I always find it was a good idea to write out these numbers as I read through the questions. In general, back in my test-taking school days. So let's write all those numbers down, because they may come in handy. Oh, okay. Let's also use the notation x bar. X bar is the sample mean, whereas mu is the population mean. So x bar is 122 millimeters of mercury. The standard deviation, that's S, is 15 millimeters of mercury. Okay, so some corporation is investigating whether the mean systolic blood pressure of its employees is greater than the reported national mean. Oh, sorry. Actually, these should be mu, and because these are the population. So that's important. That's the population we're comparing our sample of employees to. Okay, so random sample of 100 employees will be selected. Blood pressure of each employee in the sample will be measured. Sample mean will be calculated. Okay, so we consider the following hypotheses. The null hypothesis is that the mean systolic blood pressure of all employees is not different from the national mean of 122, and the alternative is that the employee mean is greater than the national mean. So describe the type 2 error in the context of the hypothesis test. Okay, so yeah, I remember being so confused about the difference between type 1 and type 2 errors for the longest time. Honestly, I think the only way to like get that in your head is to just keep on doing it until it becomes second nature. There are a lot of like mnemonics out there. I don't actively use these mnemonics anymore because I just know what type 1 and type 2 error is. Basically, type 1 error is the probability that you reject the null hypothesis when, if in fact, you shouldn't have. So it means that you've rejected the null hypothesis because you think you found something, but really that something wasn't true. And then on the other hand, type 2 error is when you fail to reject the null hypothesis. So it means you come to the conclusion that, oh, there's nothing here, there's nothing significant happening here, when in reality there is something significant happening there. And of course, we never know what that ground truth is. We never know what the reality is. So that's we quantify it in terms of type 1 and type 2 error. So let's write out all the things I just said. So basically, more succinctly, type 2 error is when we fail to reject null hypothesis when in reality alternative hypothesis is true, which we never know. So in this particular case, it's when basically like so if we write out the alternative and null hypotheses, a type 2 error would be concluding that, so failing to reject, so concluding that the mean employee systolic blood pressure is not higher than the national, when in reality the mean employee blood pressure is higher than the national blood pressure, mean blood pressure. So that would be a type 2 error. Part B is assume that sigma, the standard deviation of blood pressure of all employees at the corporation, is 15. Okay, we wrote that down already. If mu equals 122, the sampling distribution of the sample mean for samples of size 100 is approximately normal, with a mean of 122. So let's write this down. And a standard deviation. So now this is the sample standard deviation of 1.5. What values of the sample mean would represent sufficient evidence to reject the null hypothesis at the significance level of alpha equals 0.05? Okay, so Oh, and then we also have this information of n equals 100. So I think here, so basically it's asking, okay, yeah, what values of this would lead us to reject this in the context of a hypothesis test? So there's an equation that's pretty common. I'm sort of just gonna write this down. Yeah, I think this equation is definitely in the formula sheet, but I just sort of knew this because it's a common sort of equation that you use when you're doing a hypothesis test for means, and you can use this equation to sort of derive a lot of the values that are represented in this equation. So we're interested in this x bar value. That's what we want to find. So I think if we, oh, also another important piece of information. This is something that again you kind of just have to know. Z is going to be 1.64 for 95% one-sided. So that's important because remember, I don't know if you guys remember, but earlier in the video, I said that Z was 1.96 for a 95% confidence interval for a proportion. And that's true, but that was because we were doing a two-sided test. We were interested in either direction of whether that proportion was different. So it could either be lower or higher. But here, our alternative is that we're only concerned if it's higher than the national mean of 122, not that it's higher or lower. So our Z statistic is going to be 1.64 accordingly. So I think at this point we can just plug in all our numbers. So 1.64 equals x bar, which we don't know, times this would be the population mean of 122 divided by our sigma, which was given to be 15, all over the square root of 100. And yeah, I'm gonna fast forward through the math. So we end up getting x squared equals 124.5. But actually, I think I should have done, oh, okay, so actually it should be an inequality because we just need at least 124.5 to be able to reject the null. So you can imagine, like, if we have 200, that would be sufficient to reject the null because a higher sample mean, like the greater the difference between our sample mean and this national mean, the smaller that, or the larger that test statistic will be. So let me just write this out. So as x bar increases, as our mean increases, our test statistic will decrease, and our p-value, our corresponding p-value, will also decrease. Oh, sorry. Increase. There we go. So that's pretty much the relationship. So I think, yeah, that's going to be our answer. Okay, part C. Using the actual mean of 125 and the results from part B, determine the probability that the null hypothesis would be rejected. So let's see. So now our actual mean, we're going to call this actual, is 125, so it's not 122. So I think what we can do, so it's asking, okay, probability, I think this is a probability question. So probability that the null hypothesis will be rejected. So from our previous answer, we determined that that's the sample mean necessary to reject the null hypothesis. We can rewrite this as this. So this is pretty much similar to the equation that we had before, where now we're trying to determine what is this probability that we reject the null hypothesis if this actual mean is different, if we've updated our knowledge about this actual mean. So it's going to be 124. Oh, let me put this in a probability. 124.5 minus 125 divided by 15. Oh, hold on. Oh, I forgot the divided by n, so that's divided by 100. And that gives us okay, actually thinking about it, because I'm looking at this equation, I think I'm doing something wrong. So let me reread this question. Using the actual mean of 125 and the results from part B, determine the probability that the null hypothesis will be rejected. So, okay, let me erase this. So it's asking, okay, what is the probability that, so this is the null hypothesis being rejected from our previous answer, part B. So I think what it's asking is, okay, if we had, assuming that this 124.5 value is what it takes, is the sample size that it takes to reject the null, but now that we have to compare it to this new population mean of 125, how likely still is that 124.5 value as the threshold sample size needed to reject the null hypothesis? So I think, okay, I'm just gonna like write some stuff on the side here. I think we have to update our value. So that's going to be 124.5 minus 125 all over 15 divided by, okay, and then some math. Some math is done. Okay, and then we get 0. What is this? Negative 0.355. So this value is our updated value now to reject the null. It's updated because we have this new population mean. So I think now it's asking, okay, if we have this new z, anything that is greater than this z, let's call this z star. Anything that's greater than this like z star value is going to be rejected, or if we get a value that's greater than it, then we're going to reject the null hypothesis. So I think what this question is asking is, what is the probability that we get something greater than this updated value? So I think, so okay, I'll tell you, like in my daily job, there's a function in R that you can just plug it in. It's like p norm. You plug in your z statistic that you calculate into this p norm, and it spits out a probability. So I don't know what the equivalent function of that is on the calculator, but I don't have a calculator, so apologies for that, but I'm just gonna go ahead and plug it into R, and I'll be right back. Okay, so I get 0.355 0.64. So that means that the probability of rejecting the null hypothesis using this updated mean of 125 is 0.64. I think that's the right answer. I think this is the hardest question so far, to me at least, just because in my day-to-day, I don't really deal with, or like, in the things I've done before, I've never had to deal with like an updated mean. Like the data I had was always the data I had. So I never had to deal with that. So I think this is the way to do it. I'm not sure though. But anyway, let's move forward. What statistical term is used for the probability found in part C? Really, okay, so it's asking what statistical term is used for the probability to reject a null hypothesis. That's straight up a definition. That's power. That's just, you just got to know that definition. I'm pretty sure, yeah, it's power. Okay, moving on. Suppose the size of the sample of employees to be selected is greater than 100. Would the probability of rejecting the null hypothesis be greater than, less than, or equal to the probability calculated in part C? Explain your reasoning. Okay, so this is where knowledge of that equation that I talked about, this x bar minus mu over standard deviation divided by square root of n equals z. Yeah, this equation is super helpful when it comes to determining relationships between all these variables. So basically it's asking if x bar increases, if n increases, right, because it's the sample of employees greater than 100, what would the probability of rejecting z? So how do you write that out? So the probability, so you plug in this z, rejection is under 0.05. So what happens to that value as n increases? So I think one important thing to note is, and this is just a relationship that, it's one of those things that you just got to know. There are definitely ways to prove it mathematically, but I think at the AP Stats level, a common sort of train of reasoning is that as your sample size increases, your standard deviation decreases. So that corresponds to this sigma term. And the reason for that is the more people you have, the less variability you're going to have, because you just have so one way to sort of illustrate this is if you had like a normal distribution, the more people you have, so this red will indicate the more people, the tighter that distribution becomes, the closer around the true mean that distribution becomes. So going back to this relationship, or this train of thought that we have going on, as n increases, our standard deviation of the distribution of sample means will decrease. So that also means that the minimum value of our mean that we need to reject the null hypothesis will also decrease, because again, the difference it takes between the sample mean that you observe and the population mean, the difference it takes to conclude that something is statistically significant decreases once you have more people, because again, that distribution is getting tighter. So when we have a lower x bar, so if we sort of look back at our equation here, so it's decrease minus, and this stays the same, decrease over increase. So this is a pretty informal way, but I like thinking of it in this way because you can use this to predict what the value or the magnitude of the value of z, you can predict what it will be. So this denominator, this bottom part, so when you have a fraction where the numerator is shrinking and the denominator is going up, that value is going to be really small. So this is going to be very small. It's going to be a very small value. And when you have an x bar that's getting further away from the population mean, so mu, so you can even like plug in some numbers here. So like if our mu is like 5 and our x bar is like 2, and that x bar suddenly goes down to like 0.1, this is going to be like the magnitude of 0.1 minus 5 is going to be bigger than the magnitude of 2 minus 5. So this is going to be increasing. So when you have now this fraction where the numerator is getting bigger and the denominator is getting smaller, that will result in an overall value that gets bigger. So I hope you followed that. I know that's a little bit confusing. That's how it makes sense in my mind. But basically what that means is our z value is getting bigger. And when we plug it back in... Okay, sorry, my battery actually died there because, yeah, this video is taking super long. This test is taking a really long time to complete. Basically what I was saying was that, yeah, if my train of thought makes sense, then ultimately, as the z-score gets bigger, then when we plug it into this p-norm or something that generates a probability from a z-score, that is going to be smaller. So it means that because our p-value is getting smaller, the probability of rejecting the null increases. So yeah, I know that was a lot in the train of thought, but that's how you sort of approach problems like that. It's knowing the relationship between each of these variables based on this super useful equation. And that is the end of the test. So we finished the free response section of the AP Stats exam. Not gonna lie, I'm pretty tired. That test definitely wasn't like a super easy, stroll in the park. Like I definitely had to think a lot. And yeah, I'm not gonna show you exactly how I scored because I don't want to go through all the trouble of scoring it, but I did sort of flip through the answers, and I think for the most part, as far as I can tell, I think I pretty much got everything. You guys can double check it, but I think overall my takeaway from this experience is that statistics is really hard, and a lot of the stuff that as data scientists or statisticians or whatever, a lot of stuff that we think about is stuff that's actually taught in AP Stats. It's taught from the beginning, how to appropriately interpret your results and say the right things. So there was a lot of careful language that we have to use when talking about our results. And I think the AP Stats exam really tries to get at that, because if you don't use super careful language, you're not going to get full points for that question. So it's all about writing down everything that you can think of that would sort of make your answer as complete as possible. That being said, statistics is really hard. It's a really hard subject, but I think it's super useful. I mean, I think a testament to that is, these questions that were asked in the AP Stats exam, I still think about these things like every day. Like I still use a lot of these concepts. Whereas if you think about like AP Calculus, like I don't use calculus in my day-to-day, and I think unless you're a mathematician or I don't know, an engineer or something, like you're not going to be using calculus. But with statistics, like statistics is everywhere, and it's really important to know, to have high statistical literacy, to be able to navigate around what's real and what's not real, especially in our current day and age of fake news and sort of sensationalized headlines, it's really important to be able to tell when something is valid and when something isn't. So I think AP Stats as a class, as a course, is really helpful, and I think that this exam is actually a really good representation of sort of the basic statistical skills that you need to know to be able to, just to be able to live in our current day and age. And I hope you guys enjoyed that. I don't know, it's literally me taking an exam, so who knows. But I had a lot of fun taking it. I definitely, jogged my memory a lot of times with these things, and it was good for me to sort of revisit these fundamental concepts. So if you like that kind of stuff, let me know, and maybe I'll do some more stuff like that. I don't know. I think it'd be really exciting and fun. Otherwise, stay tuned. Leave me a comment. I love reading your guys' comments and responding to them, or DM me on Instagram. I also love that too. And yeah, just keep staying engaged, keep staying with me. And if you like this stuff, don't forget to subscribe. And I'll see you guys soon in another video. Peace.